welcome to another lecture on linear programming. Last time we were looking at the max flow min-cut duality. What I mean by that is we saw these two problems, max flow as well as min-cut, realized that max flow was a what kind of program? It was a linear program directly, right? And then we saw a very related but a very distinct problem called min-cut. It could be formulated as an integer linear program, right? So this was a linear program where we had to put in specific constraint that a particular variable is going to be integer. Then it becomes an integer linear program. Now, this integer linear programs or integer programs is a different beast, and I would say a difficult beast, in the sense that once you formulate your programming as a linear program, you should start dancing with joy already, right? It's a linear program, you know a lot about it. You write it as ILP, you're like, okay, what's the big deal about it, right? The reason last time I emphasized there are problems which are very, very difficult and can be formulated as an integer linear program. Okay, so now what to do with this? This doesn't help. Mostly the strategy is you take this integer linear program and convert it into a linear program. What do I mean by convert? My problem doesn't remain exactly the same, it's a different problem. It's a relaxation of my original linear program. So I'm not saying, so this is equality, this is equality, this I don't know. And the entire game to be played is, what can I say about the relation between this ILP and this LP, right? Yes. For the case of max flow and min-cut problem, this turns out to be great. What do I mean by great? By using some argument which relied on complementary slackness. It was not simply complementary slackness. Because of this nature of this problem and properties of complementary slackness, we can actually prove that these two, so this follows by linear programming, but actually all three are equal. Okay, and if you remember, what we did was, we took a solution here. Using that solution, we were able to generate a cut of the same value. So the optimal solution here produces a solution here which had the same value. Correct? This is what we were able to achieve. Okay, so now this proves that these three are equal. In effect, for max flow problem, this is equality, right? And what we'll be dealing with in future is, when we relax these integer programs, what can we say about it? And what happens in general? Is it equality? Is it not equality? Is it a good approximation? This depends on the situation. This depends on the context. And we will see multiple such contexts. Okay? So this relaxation rounding technique has been a success in last 20 years. In many, many cases, there are many, many papers which do this technique. Okay? And I hope by the end of 2-3 weeks, you would know what I mean. What is this relaxation rounding? For today, we take a detour. For today, what we are interested in is, even if you have seen this complementary slackness condition, you might say that, oh, this should somehow help me in finding a solution. It is telling me what conditions to put to find my optimal solution. So, can I use these to find my solution easily? What we are going to do today is learn this generic approach to solve linear programming. Okay? First important thing is, this is an approach. This is not an algorithm. This is not like simplex algorithm. I will outline the approach, and then in some cases this will bear fruit, in some cases it won't. Okay, that's why I'm calling it an approach not an algorithm like simplex or ellipsoid or interior point. Okay, so in some cases this helps us, in some cases it doesn't. One of the cases where it helps us is max flow min cut. So plan for today is understand this approach, this very nice intuitive approach. Once we understand the approach, then actually ask, can we apply it to one case? And we will see that when we apply it to this, you obtain what we call Ford-Fulkerson algorithm. You might have heard of Ford-Fulkerson or Edmonds-Karp or whatever. There are multiple names, variations, but that is what. And this is like augmenting paths. If you have heard of these terms, you would have learned this in algorithms course. Cool? The idea is clear what we are going to do today. Let us start. And since I want to torture you, first question is to tell me what is the dual. So, sorry? Go ahead. Senior people who are very smart can also figure out what is the dual. Or if you want to tell me directly, please go ahead. I would be happy. Okay. So, minimize. Okay. Okay. Good. So now you are getting a hang of these things, right? So I have to make things more complicated. I will. Okay. So this kind of duals now you can very nicely take. You don't have to convert into standard form and all that. You realize y is the variable here. I have to put a constraint because of the variable x here. That is this constraint, and this comes up because of less than equal to. Right? Good. And now the primal dual approach starts with a solution, not an optimal solution obviously, otherwise nothing to do. Some solution of primal, right? And this we will assume, we will say, okay, assume b is greater than 0 for this discussion, so that we already have a solution of primal. Okay? So now, once we have a solution of primal, what we know is that, so okay, again, idea is, can we improve x, right? But now, using complementary slackness condition, what we know is that a dual solution will only be positive or non-zero if this condition is loose, right? So x is not optimal, but if x was optimal, it would have satisfied complementary slackness, right? If it had satisfied complementary slackness, then the corresponding dual, there is no corresponding dual as such, but let's again, this is on heuristic intuitive picture, the y would only have non-zero coordinates where this constraint is not tight. Correct? So then we are not going to find a dual solution. What we are going to solve is will be some y which is almost a dual solution. It's not going to be a dual solution. Okay? So we are going to write the restricted dual. Okay? So the idea is, and this restricted dual will not be used in the algorithm at all. Okay, I'm not going to, and even in the formal proof, I don't have to talk about restricted dual. It's just for the idea. Okay, so what is going to happen is, I realize that if there was a y which was optimal, then they would have satisfied complementary slackness, then my y would have been of some form. That will give us restricted dual, and whenever we have a linear program, what do we do with it? Take its dual again. So now we will take the restricted primal, which is obviously not going to be this. The restricted primal will allow us to improve our solution X. Okay. So let's see. Let me write out restricted dual. You will see the idea. So let S be the set of indices such that so let S be the set where do I want it to be tight or do I? So constraint and primal. Constraints satisfied exactly. Right? So these are the ones where Ax is actually equal to B. Okay? So I will assume M constraints and N variables. Okay? So then my restricted dual so this Y again is not going to be exact. There's not going to be a feasible solution because we are trying to artificially let it satisfy complementary slackness. So this is the slack in that. And this is for all constraints. But the actual thing which is interesting is that my Yj is only equal to 0 for all j in S. Remember, S is a subset of M. For everything else, Yj is equal to 0. Exactly. So when this is tight, the corresponding variable could be loose. Remember that their multiplication is equal to 0. Intuitively, what happens is this constraint times the variable is equal to 0. So if this is tight, you have already gotten a 0, then other thing could be anything. If this is not 0, then you know that the corresponding constraint has to be, corresponding variable has to be 0. So this is kind of our solution. And to make our objective function easy, we will say that our error is just on one side. Okay, so this is just trying to artificially force complementary slackness conditions. But then, yes.
Why are we assuming Zi?
Yeah, I'm going to answer. So because again, this is all heuristic. It turns out that when we take the restricted primal, it helps us in this case. Now, since Zi is greater than or equal to 0, there is a nice quantity which I should optimize here. What do you think is that quantity? Summation Zi. If I had not put Zi greater than or equal to 0, then I will have nothing to write here. Right? So restricted dual in some sense is saying, let's find the best possible complementary or the dual solution which has S less an error, which is close to feasible. This close to feasible is captured by the minimization. And again, I am not saying that this is the LP to solve. What I am saying is intuitively it makes sense. In some cases it helps. So there is no formal proof here. It's not like this is the only way to do it. There might be different ways. This is one such way. Right? And now, will you tell me the dual? Now probably you might need a pen and paper. So this is not really a constraint, right? You can remove this constraint and you can say that, okay, what you will remember is that you have only cardinality of S many variables. right? So that means there is only just one constraint. Sorry, one set of constraints. There are n these constraints, and I have cardinality of s many cardinality of s plus 1 z. Wait, what am I doing? S plus cardinality of s plus m many variables, n many variables, right? N of these at cardinality of s many yi's. So that means the variable here is x. This is the constraint corresponding to constraint corresponding to yj. So how many of these constraints will be there? Mod s, right. So this is for all j element of s. Correct? What is the constraint for zi? That's easy actually. Remember what we used to do to take the dual. Okay, one suggestion was, how many people agree? Oh, you are saying, okay, another option is zi xi less than summation zi. Okay, this definitely is of the wrong form, right? Zi could not be present in the dual. So you are forgetting how we take the dual. So this is wrong. That is why a pen and paper sometimes help. This is also wrong. If you are not convinced, which variable does this correspond to? Yes. Right? There is no variable which this could correspond to, right? So what will happen is, you will have constraint corresponding to zi. So the constraint is xi less than equal to 1 for all I. Okay, and xi greater than equal to 0. No, because equality. So sounds good. This is my restricted dual. Okay. And now, let's say we solve this problem. Okay, it could either be infeasible, or if it is feasible, it will have some solution, right? So one option is, now once we have the restricted primal, one option is it is infeasible. Why can't it be infeasible? Huh? X equal to 0 satisfies it. No, it depends on the signs in this AJ star, no? Why can't AJ be negative? AJ star be negative? Oh, greater than equal to 0. Ah, right. So, correct, yeah. So it has a feasible solution. Great. So, can't. Good. Now, the 2 points which we will observe is, suppose it has a solution. Let's say XR is a solution. Okay, then what you can show is that X plus theta XR is going to be a feasible solution with better objective value. Sorry? Oh, X was your solution of the primal. This is what you were started with, right? This is what you wanted to improve. And what this shows is that this, the solution of this, if you have a solution of this will allow you to improve. Actually, if I want to be completely correct, remember this, right? What do we know about this dual? What is its, can you give a lower bound on its value? Yes, object, there is only one value associated with the 0, right? It cannot be 0. If it is 0, what does it mean? What does it mean by perfect? Exactly. No, not primal. X is optimal. Right? That's what you want to say. Correct? So that is awesome. If the value here is 0, it is designed in such a way that this is optimal. That means if this is 0, then X is optimal. If this is greater than 0, then, and then I have given this as a small exercise, but there is nothing much to check. We have a C transpose X which is positive. So if I do this, this will obviously be, it will increase C transpose X. And now, what do we know? Here, there was a gap. So now I can use theta to multiply it and have some, and there's something which I think in mid-sem also there was a question, right? So you kind of increase theta so much. In the simplex method, we also do the same thing. We just increase theta so much so that no constraint is violated, right? So these tricks are old. But again, I'm giving you the intuition that this will be an improvement. How much of an improvement, all that, I'm not specifying. Again, because this is a heuristic. In some cases, this will be a great algorithm, and sometimes it is not. Okay? And another thing you can show is that if X is not optimal, implies there exists an XR with objective value strictly greater than 0. Okay? And that is not hard. What you can show is that if take the optimal solution, you look at the difference between the optimal solution and X and just scale in that direction. That is going to be your XR. So I think I have gotten one direction wrong. What will happen is I want to make sure that so probably this would be greater than equal to 0 or something. It should be the opposing direction. So this yeah, there has to be an opposing direction. So I don't remember which way, where it is. Probably it is greater than. But what will happen is that this theta will stop. Like as you increase theta, this constraint will be violated if your theta is very large, right? And that is why you have specifically looked at only those j's where there was a gap, right? So I think this has to be the correct one. I will correct my notes, and you can probably verify, right? Huh? Oh, the point Pratyush was raising was, if I write the solution like this, and if my restricted primal was like that, even if I take theta is equal to infinity, it will still remain feasible. Because you have only this constraint, and as you add more and more x, this is becoming more and more negative. So if it was satisfying ax less than equal to b before, it will keep satisfying ax less than equal to b before. And then on the top of that, if theta is infinity, then this objective value will become infinity. So clearly, huh? It is, thank you. So, good. That's why you should know how to take the dual, even if your instructor doesn't, right? Okay, so yeah, if you think about it, because this is going from minimization to maximization, this has to be greater than equal to 0. Okay, so that means, see again, remember the big picture. The exact reason why you had chosen these constraints were so that there is a gap between those constraints and 0. So you have a gap, you have some freedom to move around. And even though this is greater than equal to 0, since we have freedom to move, there is some small theta I can use so that this is still feasible. Okay? Makes sense? So the entire big picture remains exactly the same. You are using this, and if you have the correct sign here, it will stop you from making theta infinity. Okay? Good. And this will make sure that you always have a direction to improve. Correct? Now, at this point, I have not given you any guarantee about how much this improvement will be. It might happen that first time my improvement is half, then 1 by 4, then 1 by 8, and so on and so forth, and I might not even get closer to the optimum. Right? So all those guarantees are not there. And I'm not going to give you those guarantees because this is an approach. This is an approach. This is not an algorithm. In simplex algorithms, we are moving from vertex to vertex.
Taking out, switching across combinations of tight conditions.
Right? But here, as you move about, I would assume that whatever was tight before will remain tight. And you will get more and more tight constraints or something. I don't, but yeah, actually, yes. Yeah. Right? Right now I'm thinking probably, so I think the definition of S, I think we should write the dual exactly first. Tell me what is the dual. Is it greater than equal to 0 or less than equal to 0?
Cannot be less than equal to 0.
No. See, remember, these are only some of the constraints. No. See, because remember, these are not the entire constraints, right? There's only S many constraints. What about the other constraints?
The XR that you get, you set the rest to 0, that does not cause any problems when you come to the X.
No. So something here was saying AX was minus 2, right? Right? Now when you do X plus theta XR, what happened to those constraints? Will that constraint still remain satisfied? We have no.
Has only those variables. This essentially ignores a lot of the variables. So in XR, when you want to stretch it out, we set those to 0.
No. You are confusing between constraints and variables. The constraints will remain. I'm constructing a new feasible solution for the primal, right? XR, the variables are less. Constraints are the same.
In the restrictive primal, we have mod S number of variables for XR.
We have mod S many variables. X corresponds to, no, we have n many variables.
The restricted primal, not the restricted.
In the restricted primal, we have n many variables, right? Because there are n many constraints here. And again, you are confusing between the number of variables we have restricted are in the dual, not in the primal. Right? Okay. So once again, tell me, I think it should be less than equal to 0. Right. So again, the small thing was what will stop theta from going to infinity. Okay? Something has to. And that is what I am telling you. Remember, there are some constraints here which are exactly satisfied. And for some constraints there is a gap. In the restricted primal, with X, we have no guarantee over those constraints which had a gap. Here, for the constraints in S, we have a guarantee that this thing is less than equal to 0. For the constraints in M minus S, we have no guarantee about X. What I'm trying to say is, if J is in M minus S, we have no control over this quantity. Agreed? Because we have only constraints here. But what we know for these J's is we have a gap. If for all of them, if this thing was negative, then probably yes, the actual value of the primal was infinity. But my point is, what will happen in most of the cases is that one of these things will actually be positive. With XR, one of these things will be positive. And now, when you take theta, as you increase theta, initially for that particular J, you had value -2, then it will become -1, and then 0 will stop it. Because this has to satisfy all M many constraints here. Once again, the overall picture is the same, which is that this is going to be our new solution. The only confusion was there should be something which stops theta to become infinite, right? So now I'm saying this is a feasible solution, right? So what do I need to check? This is satisfied. So let's do it. Since now the role of state dual is over. Sorry, Xi? That was just like artifact of dual. Right? So when you want to prove, and that's why probably I gave it as an exercise, I want to show that this is a feasible solution of this LP, correct? So then what I'm saying is I have three cases. J is element of S, AJ star transpose X should be less than equal to BJ and I want that C transpose X, correct? If I want X plus theta XR to be a better solution, it should be feasible, which is conditions 1 and 2, and then it should give me a better objective value, which is condition 3. This is fine, right? If I want to show X plus theta XR is a better solution here, I want to satisfy these three things. Now, this is feasible, this is objective value. Okay? And now, what do I know about XR? I know about XR that this is less than equal to 0 for just in S. So, in S, what did we know about X? This condition was equal to 0. XR will only make it negative. This is fine. Everything is linear. That's great, right? So with X, this was actually equal to Bj. With adding XR, this was negative. So we are fine in this case. Okay? This is the constraint which will stop from making theta infinite. Because here, we know that there is a gap. This is not exactly equal to Bj. But as you start increasing theta, this might get violated. Right? So these constraints, so whatever is the gap divided by theta, in some sense, the minimum over that, that would be the theta you will pick. So this from in most cases, when it doesn't stop it, your primal probably had, not probably, your primal had the objective value to be infinity. So it's okay. And this is very easy. It is just because C transpose XR is also positive. This, see, equal to 0, it can't happen. That means you're already at the optimal. We will stop. So this is, actually you are getting some increase. Right? So probably this makes things more clearer because we made a mistake, then corrected it ourselves. So, sorry? This positive. Again, if this is 0, then I'm at the optimal, right? We remember the restricted dual was only optimal when the value was 0. Right? So then we have nothing to do. Okay? Good. So this was the overview. Now let's apply it. Okay? If we want to encapsulate our approach, we had an original primal, we had a feasible solution for it. Using complementary slackness, we construct a restricted dual. Remember, restricted dual is a function of the feasible solution. You can't say, give me the restricted dual for max flow. That doesn't make sense. Give me the restricted dual for max flow when my objective, my feasible solution is X. Then only I decide this. So this takes a feasible solution, looks at complementary slackness, and creates a restricted dual. Correct? And now, how do we go from this to this? Yes, this is the standard duality which none of us understand and always get it wrong. Okay? So that means a lot of questions on taking duals. Right? This gives us restricted primal. And why are we happy about restricted primal? Because there is this relation that the solution of restricted primal allows us to not update, improve the original solution. And I'm writing this one-to-one in the sense that if this is not optimal, there will be a feasible solution here. If this is optimal, the feasible solution will have value 0. Okay? This is the overview. Sorry? Oh, complexity. And if you think about it, what have you done? You have converted solving an LP into solving another LP. So this solution is only, so it's a good question. This is only helpful if somehow we have a better complex, optimized thing to solve restricted primal.
Even exponential time, does it get to the solution even exponential time, or there's no guarantee of that?
Oh, you mean here?
For
it might not, like it can be like this 1 plus half plus 1 by 4. If your strategy of solving restricted primal is very stupid, then yes. So it's the game is about whether this restricted primal, can you get intelligent solution for that, and that we will see in the next flow. Okay. Then we have to show that that converges. I'm not that good in analysis, so I will leave it to you to prove. Yeah. So again, this will only be helpful if somehow the restricted primal is easier to manage as compared to original primal, and this will happen in the max flow case.